A very, very warm welcome to Jaideep Mukherjee, sir. Most welcome to you, sir. Friends, we have Jaideep Mukherjee, the prime force behind this particular webinar, Director NASA FSGC, who has just joined. Welcome, Jaideep. Good morning to you, Jaideep.
Morning.
Very good morning. Jaideep, we have a good number of participants also signing up in the live stream YouTube, and
Okay.
some are signing up in the Zoom. So we have about 7 or 8 participants in the Zoom now, and about 7 to 10 who have signed up in the YouTube, and the numbers are slowly increasing. Thank you for your support. Thank you for joining in.
No problem. I noticed that there was no question and answer after Pradeep's talk. So I'll just talk for 5 minutes in the end, and if there are questions, first we'll open the floor for questions. If there are no questions, then I can talk. Yeah.
Sure. As we discussed, we will make sure that there is questions after every speaker.
Yeah, that's a better thing. Yeah.
Welcome, Jonah. We welcome Jonah, who has just joined in. Jonah is a speaker. Welcome to you, Jonah. Jonah, we have made you a co-host, and Jaideep sir is also a co-host.
Okay, I'm good. Good morning or good evening.
Most welcome. Good morning and good evening for friends in India. Thank you for joining in.
Thank you for inviting me.
We have a good number of participants signing in the Zoom, and some are joining in the live stream, YouTube live stream. So we are doing good on time. We should be able to start in the next 5 to 6 minutes.
Thank you.
Thank you. Good morning again, Jaydeep. We have all the speakers who have joined. We have Dr. Pradeep Shinde, who has just signed in. We have Mr. Nityasri Murugan, who has joined in, along with Jonna Ocampo. Welcome to Dr. Pradeep Shinde. Welcome to Mr. Nityasri Murugan. So, again, greetings to all the participants. We are dot on time, 6:30 p.m. in India now, and 9 a.m. at Orlando. Jaydeep, I think we should start. Can we?
Yes, are you expecting more people to join?
Yeah. But then the initial remarks and then the customary thing, that
Okay.
will.
Yeah, go ahead, start then.
Thank you, Jaydeep. Greetings to all the participants. A very good morning to friends in USA and good evening to friends in India. Explore the Space is very delighted to have the presence of all of you for the second edition of Indo-US Youth Space Talent. The project had been inaugurated by Dr. A.S. Kiran Kumar, former chairman of ISRO. That was a great encouragement for us. And we had the first edition on 10th of July, where we had participants from University of California, Davis. This time we have the solid support of Dr. Jaydeep Mukherjee. We have speakers in Jonna Ocampo, Dr. Pradeep Shinde, and Mr. Nityasri Murugan from IIT Madras. Participants, the very idea of having this particular project is to identify, showcase, and celebrate youth talent in space industry in India and United States of America. With that much, I would like my colleague Suresh to play the inaugural address of Dr. Kiran Kumar, former chairman ISRO. Over to you, Suresh.
Ladies and gentlemen, greetings to all of you. I am pleased to inaugurate this interesting series of Indo US Youth Space Talent, a series of programs planned in India and USA to promote further cooperation between India and USA in space education, research, and industry. Space Tutor, Explore the Space has joined hands with University of California, Davis, USA, and MATSI Innovations, USA in doing this very interesting program. It is heartening to note that the partnership between India and USA is on a steady growth path as ties continue to expand between the two countries. Space industry collaboration in particular and economic are very promising and interesting to note. Science and technology cooperation between USA and India strengthens our bilateral relationship, promotes economic growth, and allows us to develop new and innovative technologies and products to address. The United States and India believe that science, technology, and innovation are key tools that will help us address global challenges, which include climate change, health, education, food, water, and energy security. Both countries support cutting edge research and are building public private partnerships that promote science and technology based in innovation and entrepreneurship. The United States and India also recognize the importance of gender equality in scientific workforce and have conducted numerous exchanges to encourage increased participation of women and girls in science. The two countries have taken significant steps in advancing the private sector. The endeavors will shape the impact US and Indian space policies and programs over the next decade. Recently, India and US have agreed on advanced space collaboration and cooperation in several areas under the Initiatives on Critical and Emerging Technologies umbrella. And this comes at a crucial time for both countries. This follows from the meeting of the US India Civil Space Joint Working Group, which was held in January 2023. The solutions to induce long-term cooperation is to sustain engagement between academics, private sector, and state-led entities in the two countries. It could also take the form of collaborating on highly specialized projects such as NASA ISRO Synthetic Aperture Radar mission. India and USA are adopting many novel approaches in new space age to achieve a very significant and meaningful partnership. More Indian students travel to USA and back and forth with ease, and this is something that needs encouragement. India and USA are also working on a very advanced NASA ISRO Synthetic Aperture Radar mission, which enables measurements and causes of consequences of land surface changes using advanced radar imaging. This mission concept and the resulting partnership are in response to National Academy of Sciences 2007 Survey of Earth Observational Priorities for the next decade, known as the Decadal Survey. One of the top priorities identified in this survey was to gain data and insight in three earth sciences domain: ecosystems, deformation of Earth's crust, cryospheric sciences. This initiative to encourage and identify youth talent in space technology arena is a very commendable one. Tomorrow's prosperity and peace depends on how we cultivate the youth of today. I congratulate the organizers for this initiative and wish them a great success in their endeavor to enable the next generation to appreciate the rapid progress that is happening in the arena of space and how this can be used for both sustainable and progress of humanity, not only on planet Earth but also in its exploration of the universe. Wish you great success. Thank you very much.
Our sincere thanks to Mr. Kiran Kumar for his inauguration. Uh, Ladies and gentlemen, this was the speech that was recorded before the first edition of the program on 10th of July. We will be playing this inaugural speech of Dr. Kiran Kumar, which, as I mentioned, is a matter of great privilege and it's a matter of great encouragement for us. Before every program of Indo US Youth Space Talent, we will be playing this video. That was why you see the mention of UC Davis and MATC Innovations. For this edition, we have the support of University of Florida, where we have the speaker Jonah Ocampo, and we have Dr. Jaideep Mukherjee, Director, NASA FSGC, Dr. Pradeep Shinde, Founder and CEO, Space Loon, and Mr. Nitya Sri Murugan from IIT Madras. That's the line of speakers for this particular edition. Now, I have privilege and I am pleased to request Dr. Jaideep Mukherjee, Director, NASA FSGC, for his initial remarks. Over to you, Jaideep.
Thank you. I'm just going to share my screen 1 second.
Yeah.
Okay, I'm trying to play full screen, but okay, there you go. So thank you for arranging this program. This is a good time because um, India and USA have really joined together for a number of technology advancements, as Dr. Kiran Kumar mentioned in his speech. But what happened after that was that India has signed the Artemis Accord, which is nothing but a set of non-legally binding principles to guide civil space exploration. This is not legal, it's just non-legal, but it's a set of principles that they want countries to follow for the cooperation in civil exploration and the use of the moon, Mars, comets, and asteroids for peaceful purposes. So 29 nations have signed the accord. The latest one was Germany a month ago. India signed the Artemis Accord in June 24th, which is a good sign. And I know NASA is working with ISRO to train Indian astronauts to go to the space station, hopefully by the end of next year. So this is a good time to showcase what's going on in the US and in India. For the speakers today, they are part of a program called the Florida Space Grant Consortium. I'm not going to spend time on that, but it's just a voluntary association of all the universities in the state of Florida. But there are 52 such consortia in the nation, all 50 states, Puerto Rico, and District of Columbia. And there are 1,000 affiliates nationwide. This is an incredible network of universities and industries working together to address needs in education, research, and service. As I said, it's in every state of the nation. In the state of Florida, we have 22 affiliates. And here's a map which shows all the affiliates across the nation. I think it's an incredible network because we do everything from astronomy, astrophysics, engineering, whether it's civil, whether it's aerospace, whether it's mechanical, space medicine, space law, and so on. So we have a number of programs. These are all our universities. I don't want to go through it because this does not affect you a lot. But as you see, Kennedy Space Center is one of our affiliates. The Space Florida, which is a quasi-government entity, are one of our affiliates. These are the programs. Again, these are not for students in India. They're mostly for students in the US. But to give you an idea of the two students that we are going to showcase today, they went through some of our programs. So we provide fellowships and scholarships and internships to students across in the state of Florida. But what we try to do is to do joint collaborative projects, undergrads and grads. So we have launched payloads on Blue Origin. We just came back. I took a team of 3 universities. One of them was led by Dr. Pradeep Shende, and we launched weather balloons in Texas along the path of the annular eclipse. We support a senior design project. We support NASA competitions. We have the educational license of a rover the NASA Kennedy Space Center has built. And this educational rover is open. Anyone can download our 3D printing guides and they can print their own rover. The software is free of charge. Anyone in the world can do that. We also support a lot of research among faculty in the universities in Florida. We also work with Kennedy Space Center and we try to develop programs which can be commercialized, projects which can be commercialized. Just to give some examples of some of the programs, some of the interesting research programs. This is something called DART, and if you look at this red capsule at the bottom, it was built by students from 2 universities, University of Florida, University of Central Florida, led by a faculty from the University of Florida. And the idea is that in the month of August and September, there are a lot of dust storms from Africa which blow over to Florida. And these dust storms carry pathogens. And when they land on the crops, they destroy some of the crops. So we asked students to come up with an experiment where we can put this dart or this capsule underneath the wings of a F-104 fighter jet, go 30,000 feet in the air, capture some of the dust grains, the sand grains, and study the pathogens. And so that's an image of the F-104, and that you can see Kennedy Space Center below. You can see these are the two launch pads. This become very expensive. It's like, it cost me $10,000 for about 30 minutes of flight. So we switched to a World War II plane near Orlando, and we continued doing the results. And these are some of the electronics entirely done by students, mostly undergrads. Here's again another picture of the DART experiment. You can see the vehicle assembly building, and this is the shuttle runway. The another project that we do is that there's a professor called Andrew Sugar from the University of Florida. He has a Martian chamber, which is over here, and it can mimic the conditions of Mars, atmospheric conditions. And I'm not going to go into detail, but the idea is that he is testing what bacteria can survive Martian conditions. And what I last heard was he studied 30 of them, and there is one that might survive the conditions if it is in the frost, the permafrost of Mars. So a lot of students work on these projects to see which bacteria can survive Martian conditions. Another very interesting project is to see what will happen to a good bacteria under microgravity conditions. For example, in our human body, we have a lot of bacteria in the stomach, which helps us with digestion. What will happen to, and we call that a good bacteria, right, is helping us. What will happen if we go to the moon or Mars? What will happen to the bacteria? So to study that, what they did was to look at the some kind of an interaction between a microbe and an animal. The microbe is a bacteria, I cannot pronounce its name, but the animal is what is called a bob squid. It's a very small squid, mostly found in Hawaii, but it has a light organ, and this bacteria inside the light organ lights up that organ, and when it lights it up, it camouflages itself from the predators. So here's an example of a very good bacteria helping the animal, in this case is the squid. Now, what will happen if I take this bacteria and the squid to the space station? Will that bacteria be a good bacteria? So we did that. They have flown that to the space station. They're studying the effects of the bacteria on the squid to see whether it lights up the organ or not. Again, I don't want to go into details. That's for another talk. We also do a number of K-12 programs. One of them is something called Plant the Moon Challenge. We are challenging students to grow plants on simulated lunar and Martian soil, and we have some informal education programs. But I'm very interested and excited to hear from a speaker from IIT Madras, because he's going to talk about, I think, about creation of a tool using the regolith on the moon. And why I find this interesting, because in our institute, we have a NASA center called the Center for Lunar and Asteroidal Surface Sciences. Underneath that, we have something called the Axolotl Lab. It's the world's largest simulant creation. We create and manufacture lunar and Martian and asteroid regolith, and anyone can buy it from the internet. But I'm really excited to hear his talk. But just to give you a background on the two speakers, one of them, Dr. Pradeep Shinde, went through this program. He'll talk to you about his journey on how he created a company based on some technology that we helped him do some research on. And then the other speaker is Jonna Okanta, who is a student at the University of Florida, and she's an amazing student. Pradeep and Jonna are examples of a spacefront success. And Jonna, as you will hear from her talk, has done a number of things with microbiology, life sciences, even chemistry and physical sciences. But apart from that, she's also the author of 2 children's books. So what she's trying to tell you is that, you can do a number of things to be a part of the space program. So I'm going to stop here because I think Pradeep and Jonna and the IIT Madras student, I'm very sorry, I forgot your name, but I'll remember it next time. But they're going to all talk about their projects, what they're doing in India and in the US, and we hope that you can get some inspiration from what they're doing. And believe me, now there's a big, good cooperation between India and the US. There's great cooperation in India among Indian students and ISRO, which was not the case when I was growing up in India. So this is a good time to be a part of the space program. So I'm done, Venkatagiri. I'll open it up to the students.
Thank you, Jaydeep. The pictures of art were really breathtaking. Thank you for sharing the pictures. Now, ladies and gentlemen, we move to the main section of the program. I have pleasure in introducing Mr. Nitya Sri Murugan. Mr. Nitya Sri Murugan did his BTech, Bachelor's in Technology in Calicut, and then went on to do his MTech in NIT Trichy. Currently, he is pursuing his PhD in the Department of Mechanical Engineering. He is pursuing his PhD in the Department of Mechanical Engineering in IIT Madras. So we welcome you to the program, Mr. Nitya Sri Murugan. We are pleased to present Mr. Nitya Sri Murugan to the audience.
Thank you, Venkatagiri sir, for your warm welcome. And, so is my screen visible, sir?
Yes.
Yeah, okay. So warm greetings to everyone. I'm SK Nitya Sri Murugan. I'm a PhD student in the Department of Mechanical Engineering at IIT Madras. And I'm working under the supervision of Dr. Satyan Subbaya from IIT Madras. And my co-guide is Dr. Ajay Malche from Purdue University, USA. And I'm going to present on the topic in situ production of silicon carbide from lunar and Martian regolith for use as a cutting tool. And mostly in this presentation, I will be focusing on maintenance activities in space and in situ resource utilization and in space manufacturing. So here are our collaborators from Purdue University, USA. Dr. Ajay Malche, who is my co-guide, is actually a distinguished professor of mechanical engineering and agricultural and biological engineering. And Dr. Salil Bapat is a research scientist at Purdue University. And Mr. Albert John Patrick is a graduate research assistant at Purdue University. So coming to the whole space, the era of space exploration is distinguished into two space ages. One is the old space age known as Space 1.0, and the other is the new space age known as Space 2.0. So Space 1.0 starts from the early days of space exploration, starting with the launch of the first artificial satellite Sputnik 1 by the Soviet Union. And it is characterized by intense competition between the spacefaring nations. And during this space age, exploration interests include like launching of navigation and communication satellites, telescopes for astronomical observations like the Hubble Space Telescope, and scientific studies related to microgravity environment, which are performed in space station like in the International Space Station. And the major milestones during this whole space age includes the Apollo moon landings, the development of the International Space Station, and various probe missions to explore our solar system. And the majority of these space missions during the space age are undertaken mostly by international space agencies. And one of the peculiar aspects of this space age is like it is very much heavily dependent on Earth-based supply chain models, meaning like we are launching all these systems from the Earth. So this is now I want to talk about how maintenance is actually carried out in the Space 1.0. And let's take the case of the International Space Station. So in the International Space Station, there are a lot of space components or space systems. And each of its space components has its own operational lifetime. And if there is any failure of spacecraft component, then it is actually replaced by a spare mass, which is actually kept on the orbit. So, and these spares are replenished by timely resupply missions. So, for example, the estimated International Space Station maintenance logistics during the period 2012 to 2020 is shown in this figure. Here we can see like the total approximate spare mass, which is currently stored on the ground, is 18,000 kilograms. And the predicted annual average up mass is actually around 3,000 kilograms. Whereas the total approximate spare mass, which is currently on the orbit, is around 13,000 kilograms. But whereas the expected average annual failures is only around 450 kilograms. So even though the expected average annual failures is mass is comparatively less when compared to the total space mass which is currently on the orbit, but still we require these huge amount of logistics mass in order in the event of any catastrophe or in terms of any emergency, or in order to actually mitigate the risk which is involved in the operation of the International Space Station. So coming to the new space age or space 2.0. So space 2.0 is characterized by increased commercialization and the involvement of private companies. And it is associated with the emergence of new space technologies like in-space manufacturing, on-orbit servicing, and business models like the space tourism and concepts such as reusable rockets and human colonization of other planets like Mars. Space debris mitigation are in fact turning into reality from science fiction. So, and also like sustainable approaches for deep space explorations like in situ resource utilization and manufacturing in space are gaining importance. And ultimately it leads to the democratization of access to space. Here figure 4 shows the Orbital Reef, which is a private space station which is being developed by the Blue Origin company. And figure 5 shows the concept of a lunar base, which is actually visualized by the author named Show. So as envisioned by the Space 2.0, in the near term, like we will be having an extraterrestrial base on Mars or on Moon. So the key systems which are required for setting up an extraterrestrial base includes crew habitat systems, propulsion systems, power systems, surface transportation systems, mining and excavation systems, telecommunication, and food for the survival of astronauts. So launching all these systems from the Earth is quite a very daunting task. So because like for every 1 kilogram of mass, which is landed on the surface of the Mars, you need approximately 7.5 to 11 kilogram of propellant mass. So which is not a commercially viable option. So we need to have some kind of a manufacturing capability in space. So if we have a manufacturing capability in space, we can able to cover the unanticipated failure of components and thereby not being too much reliant on resupply machines. Also, like we can carry repair and maintenance activities in space, and we can also utilize the local resources available on extraterrestrial bodies like Moon, Mars, and asteroids. And also, like we can able to recycle components on board the spacecraft. Thereby the logistics mass which is associated with any given space mission is actually gets reduced. So coming to in-space manufacturing, which is currently developed, which is currently in development for enabling sustainable space exploration. So the definition of in-space manufacturing according to Skomaro et al. Is as follows. Like in-space manufacturing encompasses any endeavor which takes place outside of the Earth's atmosphere and which performs any of these 3 activities like fabrication, assembly, and integration. And the benefits of in-space manufacturing includes like it enables us to reduce the logistics mass associated with any space exploration mission, thereby enabling it to be Earth independent. And it also facilitates on-demand manufacturing, meaning like if any part gets failed, I can fabricate those components on demand. And also it eliminates the launch vehicle constraints, meaning like for example, we can able to fabricate large truck structures or large antennas in space without even considering about the constraints of the launch vehicle. And ultimately, it enables us to mitigate risk which is involved in any space exploration mission. And it also facilitates and helps to achieve in situ resource utilization. So the framework for in-space servicing, assembly, and manufacturing is shown in figure 7. Here we could see like there are 4 aspects of in-space manufacturing. So one is like it enables us to enhance the terrestrial manufacturing. And it also facilitates manufacturing in space for Earth-based applications. So, for example, like we can able to produce optical fibers in space without having any crystallization in microgravity environment, and we can actually sell those optical fibers for Earth-based applications. And the third aspect is like manufacturing in space for space, meaning like we are going to manufacture the components in space for space-based applications. And the last aspect is like extraterrestrial manufacturing to build components for outpost on any planetary surfaces or structures on any planetary surfaces by utilizing the local resources available on Moon and Mars. So in order to achieve a sustainable space exploration, we need to carry out maintenance and repair activities in space. And in-space manufacturing actually provides the key enabler, or it acts as the key enabler for carrying out repair and maintenance activities in space. And here the visualized architecture of a kind of production environment to support maintenance activity in space is shown in figure 8. So here there are two main components. One is the feedstock converter and another is the manufacturing processes. So feedstock converter is nothing but it actually converts the sources of raw materials into a required form of feedstock so that it can be used for manufacturing. So there are three major sources of feedstock in the space. So one is like we can actually source the feedstock from the earth and convert it into finished goods. Or else like we can source the in situ resources which are available on extraterrestrial bodies like Moon, Mars, and asteroids. And also like we can use the space debris which is orbiting around the Earth, and we can either reuse those or recycle into useful feedstock or repurpose those components into large structures for any kind of satellite. So these are the three major sources of feedstock, and the next major component is the manufacturing processes. So here additive manufacturing process play a very major role in actually converting the raw material into finished goods or mission specific parts. So to carry out maintenance for planetary surface exploration, and so here in situ resource utilization plays a major part. So what is actually in situ resource utilization? Here, in situ resource utilization involves any hardware or operation that harnesses and utilizes in situ resources to create products and services for robotic and human exploration. So the resources can include water, atmospheric gases, solar, wind, volatiles, metals or alloys, and it can also include trash and waste, some crew and spent landers, etc. So there are various stages to actually achieve in situ resource utilization. It starts from resource assessment. Like first we have to assess the resources in the extraterrestrial body, and then we have to acquire those resources and then process it into a usable form of feedstock, which can be used for fabrication of goods and the construction of habitats, and it can also be used to harvest energy. So the most widely abundant resource on any extraterrestrial body is its own soil, so which is termed as regolith in the literature. So here, like I'm going to speak about lunar and Martian regolith. So regolith has been defined as the unconsolidated rock material that covers the bedrock or it forms the surface of the land. Here, figure 10 shows the lunar regolith, and figure 11 shows the Martian regolith simulant, which is being procured by us from Exolith Labs. So here, like simulant is a replica of lunar or Martian soil, which actually mimics the chemical composition and physical morphology of the lunar and Martian soil. And here, like the pyroxene, plagioclase, feldspar, and olivine are the most abundant minerals which are found in lunar and Martian soil. And table 1 shows the chemical composition of lunar soil, Martian soil, and Martian simulant. So here, like we could see, it consists mostly of metal alloys, with silicon dioxide being the most abundant metal oxide. It consists mostly of metal oxides, with silicon dioxide being the most abundant metal oxide. So coming to the particle size and morphology of lunar regolith, here figure 12 and 13 shows the scanning electron microscopy images of lunar regolith simulants. Here we could see like it is mostly angular in shape, and since it's very angular in shape, like it is very much abrasive in nature. And also like figure 16 shows like almost 20% of particles lies less than 10 microns. So it is, the regolith is consists like it consists of very small particles. So all these considerations like its abrasive behavior and also the lunar dust has to be taken into account when we are actually designing systems for planetary surface explorations. And here figure 14 shows the agglutinates from the Apollo 11 samples. like agglutinates is one of the specific or characteristic feature of lunar soil, because like agglutinates are formed due to the bombardment of the meteorites on the surface of the moon, and it actually forms due to the fusion of several soil particles, and it forms agglutinates. And also glass particles are also found in the Apollo samples. And coming to the regolith processing methods which are being reported in the literature for lunar regolith. So people have tried metal extraction techniques to actually extract metals and metal alloys and also oxygen from lunar regolith. So to name a few processes, like the processes are carbothermal reduction process, hydrogen reduction of ilmenite, molten regolith electrolysis, and thermal decomposition processes. And here the main resource target was oxygen, because it is one of the key elements for life support systems, and it can also act as a propulsion element. And also from all these processes, like there are useful byproducts which we can actually tap into, and those are like iron, ferrosilicon alloy, and then aluminum and silicon elements also we can tap into. And coming to the, so for example, instead of like extracting metals, specific metals and metal alloys from the lunar regolith, people have also tried to directly use the lunar regolith into functional and to fabricate functional components from the lunar regolith. So, so they have used additive manufacturing techniques, and some of the additive manufacturing techniques which are used to fabricate lunar regolith directly is as follows. Like they have used selective solar light sintering, selective laser melting, cement contour crafting, and digital light processing and stereolithography techniques, to name a few. And people have also tried to use lunar regolith as a coating material for metal substrates, and they have used a dry aerosol deposition process for the same. And the potential applications of lunar regolith includes like we can actually source oxygen from lunar regolith, which can be used as a propulsion element and also for life support systems. And recently, Blue Origin company, they have developed solar cell prototypes from the lunar regolith. And people have also tried to fabricate regolith polymer composites from lunar regolith. And we can also construct roads and habitats using lunar regolith. And we can also able to, people have also tried to fabricate transparent glasses from lunar regolith. And they've also tried to extract ferrosilicon alloy, which can be used for fabricating structures on the moon. So the future directions for research includes like handling of powders. I mean, we have to develop technologies for handling powders in under lunar and Martian gravity environments. And we need to develop additive manufacturing techniques to process lunar regolith into functional components. And we need to optimize the metal extraction strategies for lunar and Martian environments, because like till now, all the metal extraction strategies are performed under terrestrial conditions. And also we need to develop processing techniques of lunar and Martian regolith, considering minimal reliance on products transported from Earth, like minimal reliance on binders, resins, something like that. So here is a glimpse of my thesis work. So here I intend to produce a silicon carbide from lunar and Martian regolith simulants. Since like silicon carbide is one of the hardest material, and it is commonly used as abrasives. And here are a few fascinating properties of silicon carbide, like it has high hardness, it has low thermal expansion coefficient, and it has high thermal conductivity, and it is highly resistant to corrosion and radiation, and it is a very high temperature refractory material. And here I intend to, and in my thesis work or in my PhD thesis work, I intend to produce silicon carbide from lunar and Martian regolith by reduction processes, so that I can fabricate hard cutting tools for aiding maintenance activities in space. So here figure 24 shows the comparison of the hardness values of various materials, and silicon carbide here is right up there amongst the most hardest materials known to humans. And these are my references. And I thank Venkatagiri sir for providing me this opportunity, and I thank Explore the Space team. And I also like to thank my professors, Dr. Satyen Subaya and Dr. Ajay Malshe, for their valuable inputs for my PhD.
Thank you. Thank you, Murugan. Thank you for your presentation. Now, participants, we would definitely like to encourage a few questions to speaker Mr. Murugan. Are there any questions? Suresh, can you please help? Are there any questions? Murugan, I have a question for you.
Yes, Venkatagiri sir.
As part of your PhD that you are currently pursuing, do you interact with companies in Chennai and in India? What kind of companies do you interact with? I mean, I'm just interested to know, or is it more of theory, or do you also interact with companies, industries?
No, sir. As of now, there is no company interaction. Like only we have a collaboration with Purdue University, and we do have brainstorming sessions with them. So other than that, like there are no interactions with the industry.
Okay, okay. Nice to know that. Any other question, please?
I have a question. Nithya, can I call you Nithya or is it Sri Murugan?
Yes,
Murugan.
Anyway.
Okay. I enjoyed that talk. It was great. I see a lot of one of the slides you showed. I'm curious to know whether you're a part of that project. Is using the space debris around the Earth and collecting it and using it for other electronics. Are you a part of that project or?
No, sir. I'm not part of that project. I'm actually focusing mostly on in situ resources like tapping lunar and Martian.
Okay. Yeah. I mean, and just for the other students in the audience, this manufacturing in space, additive manufacturing is a hot topic.
Yes.
There's in India, but there's in the US, because everyone wants to go to the moon. And Nithya is working on something that's going to be very useful to future astronauts or people on the moon. So that's a good project to work on. And Nithya, there are a couple of people in our institute. One of them is called Dr. Phil Metzger. He had started what is called the Swamp Works at the Kennedy Space Center. I don't know whether you've heard of Swamp Works. It's a lab which does in situ digitalization based on the moon. But he might be interested in your work, and I'll try and connect you with him. There's another person out here. He's from Nepal, but he's working on microwave sintering of the lunar regolith. So you might be interested. I'll make the connections, but you are in a topic which is a very hot topic, and everywhere in this country, and I'm sure in India too, additive manufacturing has taken a big role. This is something for students to take into account. Thanks.
Sure. Thank you.
Thank you very much, Jaydeep. Thank you for offering those connections. Ladies and gentlemen, that's exactly the purpose of this program, to act as a platform and enable connections in the space industry and academia. Are there any other questions to Murugan, please? Jaydeep, can we move to the next speaker?
Yes, please.
Thank you, Murugan. We'll get back to you. Kindly stay with us.
Sure.
Ladies and gentlemen, I have pleasure in introducing the next speaker. Our next speaker is Ms. Jonah Ocampo. Ms. Jonah Ocampo is going to speak on exploring new horizons from stimulated microgravity to a stratospheric journey beyond the carbon line. As Jaydeep mentioned in his speech, Jonah has a very, very impressive credentials. Jonah is a PhD student and a graduate research assistant at the University of Florida with a Master of Science in Molecular Medicine and a graduate certificate in biotechnology from Orsani College of Medicine. Jonah is also a children's author, and she has achieved remarkable milestones in her journey into cosmos and witnessed her non-technical payloads of Henry the astronaut take the flight on Firefly Aerospace Alpha rocket. Over to you, Jonah. Most welcome.
Good morning or good afternoon to you in India. Can everybody see my screen okay?
Yeah.
Yes, great. So today I'll be speaking about exploring new horizons from simulated microgravity to a stratospheric journey and beyond the carbon line. Throughout history, the success of missions has been based on leadership. One word for the success is teamwork. It has been recorded that the Apollo 11 lunar landing involved approximately 400,000 individuals, including engineers, technicians, and scientists. Your future as students are involving this leadership and teamwork, such as your effective communication, your adaptability, and your resilience, and problem-solving skills. I am here today to hopefully inspire the next generation for your pursuit and your dreams in aerospace. Here is the background of what I'll be speaking on today, and the different elements from biological to physical sciences and more, and a journey as for the arts. So not only is science included in this, it's also the arts. So there is a room for both artistic and scientific minds in this realm. So on ISS, everything appears to float. However, it is falling at the same rate. So 0G is actually 1 times 10 to the negative 6 G. To perform research on ISS, terrestrial analogs of microgravity environments are necessary, such as short-term parabolic flights, drop towers, bed rest studies, and also these bioreactors. So these analogs are used to study the effects of chemical, biological, and physical sciences. So why perform this microgravity research? Well, my research at the University of Florida, I'm studying microbes. And we want to really know what microbes flourish in space and how they adapt. And because they're integral in the human body and even on your skin, we want to know if this affects the health and the change, if there's changes to this bacterium, because they're commensal also with your human gut. We do not want that potential to have your body to have an infection or illness for astronauts in this closed environment. The species that I study is called Enterobacter, and it is commensal with the human microbiota. And because you are on ISS, it is there too. Also, Enterobacter genus has been found on a toilet on the International Space Station. Yet another reason to study this microorganism. As a background, in 2022, there is a study in spaceflight stressors showed changes to an astronaut's microbiome and changes also to bacterial physiology and virulence. Additionally, there are other gram-negative bacteria such as Parasitturella and Serratia maricens that's also shown changes to its physiology and virulence, increasing as a gut commensal and causing chronic inflammation, intestinal inflammation, transitioning from an opportunistic to a pathogenic one. There are other clinical implications of this with decreased diversity in the human gut. It can cause inflammation and also be related to the gut-brain connection. So when you're traveling into space, you do not want to have the problem of neurological disorders or other issues. I'm not studying in that realm, but this is another section of biology that is being looked upon. As an introduction to the species that I study, it's called Enterobacter colochi. It is a gram-negative, rod-shaped facultative anaerobe that is commensal with the human gut microbiome. It has this type 6 secretion system, and it's a way of getting into the host, such as an animal or a human. It has this paratracheous flagella surrounding the outside of the organism, and it is motile through swimming and run and tumble movements. Where this microbe exists, it's in soil, it's in wastewater, it's within the human microbiome, but it's also in this closed environment of hospitals and can cause such things as gastric wall abscesses, intra-abdominal infections, respiratory infections such as pneumonia, urinary tract infections, and in severe cases, meningitis in newborns. Now, the International Space Station is also a closed-like environment, like the hospital. And it's already been shown that your gut has altered evacuation function and decreased barrier function. So this could be a problem for long-term missions. My research involves currently is biological or in microbiology, and it involves this bioreactor called the rotating cell culture system. And it is involving these two bioreactor vessels, and one's based in a normal gravity configuration, and the other one is in what's called microgravity or low shear model microgravity, where it rotates around its axis. And doing this, we're trying to determine if this growth and physiology under these simulated microgravity conditions is a good ground model in studying how this bacteria responds in space. The spaceflight environment can lead to changes of virulence of bacteria, as I've already discussed. And the questions, will the simulated microgravity alter this physiology and virulence of this commensal bacteria when grown under these conditions of model microgravity and inverted microgravity? Currently, this is a work in progress and a manuscript in preparation. Last August 2022, I had the opportunity to be part of a team at Kennedy Space Station through the organization Star Trek Academy, and which was funded by NASA Florida Space Grant Consortium to study the environmental effects on the biological process of this microbe Enterobacter. Now, the balloon flew to the stratosphere, which is from around 11 miles to 31 miles above the Earth. And it also includes this ozone layer that protects us from radiation. The bacteria was grown up in the lab, and then it was placed in this payload box, both shielded and unshielded from radiation. Our team, which you see in the below two pictures, we're responsible in deciding which sensors should we have on this balloon. We decided in something to capture the altitude, the temperature, the pressure, and the humidity. So it's always really important to know that scientific research is not just done by one individual, it's done by many minds that come together as a team. This is the payload box that is sealed, and our team holding the balloon prior to liftoff. The bottom right picture shows about 500 feet above the ground, our GPS signal was lost. So we went out into a field using a compass of the last known coordinates, walked out about a mile in a rainstorm, and we did find the payload. So you have to understand, during these weather balloon experiments to the stratosphere, there's about a 50% chance of not actually recovering the payload. In being able to do so, we were able to take it back and to study the different conditions of the shielded and unshielded samples. And currently there is also a manuscript in process. So the impact in the end is this enhanced knowledge of this human gut commensal, this non-ionizing radiation of UVA and UVB, because we had sensors that captured that information, and also this host pathogen spaceflight studies on the immune system, because we tested these samples against macrophages, which are innate immune cells in your body, your first response to infection. It has a direct benefit to human spaceflight in LEO and extended missions. In moving on, I had the opportunity in physical sciences, in organic chemistry while I was living in Hawaii. And I was chosen for a biomedical research internship where I had to synthesize a compound, a 16 derivative compound that was an antimicrobial, an antibacterial, and antioxidant, presumably. So when this internship ended, I started a nonprofit organization called CDC's Microgravity. I ended up really loving research and had the opportunity to fly on a parabolic flight. And as I talked about earlier, parabolic flight is short-term microgravity. Wanting to see if these compounds remain robust in space. To describe the flight, it starts out about 12,000 feet and then pitches up about a 40 to 50 degree angle until it hits 16,000 feet. At that time, the pilot pulls back on the power and it pitches over. And during that time, you're experiencing about 20 to 25 seconds of microgravity. At that time, you're reaching the ceiling, everybody's floating. However, being able to take these compounds with me, I was able to take them back to Hawaii and test them. Out of the 16 derivative series, 13 remain robust. However, 3 broke apart. That is on the organic ring. 2 became not usable. 1 transitioned into an antioxidant. So you never know in spaceflight until you actually make these steps of testing. And it can be rewarding. You do not know on that day you step into the lab or into your class. But when opportunities do present themselves, please take those seriously. You do not know where that next stepping stone can be in the progress. Additionally, there is a value to your work, not just my work, your work, to astronauts and for long-term habitation on other planets. Leading me to as a children's author, I've written 2 children's books, one called On My Way to the Lilikoy Tree, which was based in Hawaii, and the other one was Henry the Astronaut, that takes us through a journey of a child's dream and going to different planets and talking about these different planets, and you learn about the composition and the makeup of these planets as you go page by page. My book was chosen as a non-technical payload by Firefly Aerospace for its initial DREAM payload on its Alpha launch rocket. And DREAM just stands for the Dedicated Research and Education Accelerator Mission, and its purpose is to inspire young people to pursue STEM education. On the top left is one of the engineers, and that is holding the book and will be placing it in the payload box that will be placed upon the rocket. The middle picture is the actual launch. And there were 2 launches. The successful launch happened last September 2022. And we had a viewing party with one of the participants that are online, Mr. Todd Cohorst and his school, and we had a viewing party for this rocket launch so that the students can participate. Now remember that the Kármán line is considered 62 miles above the Earth, and ISS is located at 250 kilometers above the Earth's surface. The bottom middle picture shows the actual video footage of the launch and achieving orbit and the release of some of the satellites. Now the book remained on the rocket. However, when the rocket, so that day Henry became an astronaut. The book flew to space. However, the book is not released into space. The rocket, when it comes down, it lands in the ocean. On that day, Henry not only became an astronaut, he became an aquanaut. So the story just keeps evolving. The top left and the bottom, the top right and the bottom right are 2 children that received this book. And it inspired one to become Buzz Lightyear for Halloween coming up, which I absolutely think is adorable. And the bottom right is a student in Brazil who received this, and the parents were very surprised at the response of their child receiving the book. I want to say thank you to everybody at this seminar. I hope you can go away and knowing you don't know where your path is going to end, but taking that first step is very important. I do have a video here that does show our balloon, weather balloon flight.
All right, we'll count down from 10. I will start it.
Oh boy. Thunder.
Are you ready?
Yep.
All right. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Thank you. And I want to thank you all for listening along.
Thank you, Jonah. Thank you for that wonderful presentation. I hope you had a wonderful balloon flight there. Donna, I have the same question. In your PhD, do you interact with companies? Do you visit companies? I'm just interested.
We don't visit companies. Most of our work is done in the lab, or through potential opportunities that are granted to us by the NASA Florida Space Grant Consortium to participate in these activities. I believe that is a really good stepping stone. It might be currently out of the scope of what the program was designed for. It's definitely something that I have interest as a student, knowing that, one day I will graduate and be part of the industry, or hopefully to be part of the industry in a continued capacity and growth. But currently, I don't think it's based upon that.
Thank you. Thank you. Any other questions, please, for Jonah?
Venkatagi, just to add to what Jonah said,
Yes, please.
space medicine is a very interesting topic, and there are a number of companies in Florida who are teaming up to send experiments to the space station. So in terms of space medicine, there are a lot of companies in Florida, and Jonah, if you're interested, I can get you in touch with them through Space Florida. That's a big thing right now. And the Center there's a organization called CASES, which supports research on the space station, and they're working very closely with companies and individuals to send space medicine or projects like Jonas to the space station. So there are opportunities.
Thank you. I definitely am interested.
Okay.
Thank you. Thank you, Jonah. Jonah, we would request you to stay back for the whole program. I'm sure there are going to be more questions. JD, can we request Dr. Pradeep Shinde now?
Yes, please.
Ladies and gentlemen, we are excited and pleased to welcome Dr. Pradeep Shinde, CEO of Space Loon, which is pioneering in mesospheric ballooning. Mr. Pradeep Shinde comes with a very, very impressive record. He has been the CEO of Space Loon from February 2018. That's about 5 years and 9 months now. Now, we request Dr. Pradeep Shinde for his presentation, please. Over to you, Dr. Shinde.
Oh, let me, did I unmute myself? Okay, yeah. Thank you for the invite, Dr. Venkatgiri. This is really great to be here. And I'm actually excited for this Indo-US Youth Space Talent thing. It's very interesting. So I thought, expressing something about our Space Loon journey. The background I will give you briefly, what exactly Space Loon is. We are trying to build the access to the mesosphere. You can see mesosphere, almost most of you are already aware of this, but I will just still say it's a region above the stratosphere and right below the Kármán line, or where the space starts. So that region provides unique access, which is almost similar to the space, but you can reach it without using the space vehicle. That is now possible with Space Loon. And we are trying to do this one for opening the market for technology testings, like other presenters, they presented their work. All of the space technologies, whatever it is that you are going to deploy in low Earth orbit or beyond, it will need to be tested. And current way of testing is either on the ground or on the ISS. So we are bridging a gap in between that. That's the mesospheric testing region. And there are a lot of other applications like Earth observation, astronomy for aerial or surveillance. All of those are possible, and many beyond that. But at this point, we are focused on space technology testings. I'm being asked this question several times over the last couple of years, that how did I start the space company, or how do I become an entrepreneur? I think this could be a relevant for this audience because this is the youth coming out from the India with the aspirations for space thing. I think it will be helpful for you. So my journey actually started when I was a student at the Florida International University. As like most of you, if you are attending this, which means all of you are extremely interested in this. So do I was when I was a student, and I was looking for an opportunities to do something related to the space. My background was mechanical engineering, and I stumbled upon this Florida Space Grant, NASA Florida Space Grant JD's program, which was the CubeSat development program. So that was a CubeSat launch initiative, almost run for almost 10 years. I participated a couple of times there. But our CubeSat, it was intended to be launched, if we win the prize, to be launched in the actual space. But it did not happen because it was a long program. And so that time we were encouraged to do weather balloon. At least we get our CubeSat that we develop as a student teams, we get it tested. So I was introduced to ballooning through that program. And I did several launches, balloon launches, testing the CubeSat, the payload that we developed, and then came across the problem. I wanted to launch the balloon to reach certain altitude. Every time I did, it never went to that altitude. It always stayed below that. And I thought maybe I'm doing something wrong. And I wanted to check. I checked with the experts and professor at the time from other aeronautical university in Florida. But it was, they said the process was correct the way I was doing. There could be some other things that we don't know yet. So while that problem was still persisting and haunting me, and then one day, actually, I was going for the lunch, and suddenly I thought there could be another way. I had that thought I thought it was the solution to the problem I was facing. And then I needed it to be verified what I'm thinking was right or not. So I developed some math, build, equation. The physics was transformed into the equation. That's what I did. And I tried tell it to the professor, explain them, they understood, and they mentioned that could be the reason that no one ever did this approach. I didn't understand what it means at that point. But it needed further validation from somebody, or how do I go to the next step? At the same time, I was doing this during my PhD, and I was graduating. And your next object is find the source of income, either job or whatever your next step is. That was the thing. My thing, I was preparing for, I will go to academia, build the research career or something. And the most important thing you need for that thing is to develop the ability that you can generate the concept and get the proposals funded. So that is the major requirement for any faculty jobs. And I was working on that thing, but I didn't have opportunity as a postdoc. You do not get to be direct to be working as a PI and get some activity. You have to work with another professor. So, but at that point, I was looking for the option to approach and build some test instrument to verify my theory. And then I reached out to National Science Foundation. They had one of the incredible program where they fund for the innovative research. It has to be game-changing and groundbreaking. That's what they focused on. And I reached out to them. I mentioned my concept to them. They responded, "This is what we fund, what you have, and it's possible, and it's never done before." And these three lines were really encouraging to me at that point, because that's one of the biggest organizations who are scientific people are the reviewers for whatever you submit, the concept or proposal either. And so I took that, but they didn't funded me because I applied for their SBR company program, and they said, you don't have a company, and you don't even have proof of concept. So I took that review and I went back to NASA FHGC, JD again, and I mentioned, look, this is what NSA has said. They're interested, and this is never been done, and it's possible. if I get the proof of concept, I told him I can build the company. So Jaydev asked me, okay, so how much do you need? I said like $200,000. And he like, that doesn't work. For this one, he gave me some funds and he mentioned, what can you do? Can you do some proof of concept, which encouraged for that research to go ahead. I did that proof of concept, and then following to that, I went back to NSF. I told them, he said, I didn't have a proof of concept and I don't have a company to build. Well, here is the proof of concept, but I don't know how to build the company. Okay, nobody that I know who knows how to build the company. So one of the NSF program manager directed me for another NSF program that takes you and a guiding line to to verify, is there a market for your company? Well, I didn't know that is the step to do. So that's what I learned. And then it followed on several different grants for the customer discovery. Then it led to us recent um, actual company building grant from NSF, as well as NOAA. We are already working on with NASA for the Eclipse project, and we're expecting few more to come through. So this is very short in this time period that I have, but it is just the beginning, and we are about to soar much in the hand. But I just like to share this with you for the reason that some of you or most of you may be wondering what should be the process, but the understanding is if you walk on the path, I think the things evolve in that direction as long as you stay there. I like to give my best wishes to this program, Indo-US partnership, and this youth talent to find their future endeavors in this region. And it's a great time for all these activities now. And these next couple of years, I will be really busy. I don't even, it's challenging for me to handle the things, but I can be accessible for you. If you need to reach out to me, please reach out to Dr. Venkat Giri and Dr. Mukherjee, and I will be able to help if possible. Thank you for your time, and it's great to be speaking with you.
Thank you. Thank you so much, Dr. Chinde. Thank you very much for your presentation. I mean, that's been a very exciting journey, and we wish you greater glory and success. Any questions for Dr. Chinde, please?
Pradeep, is there any way, without giving up your secret, can you talk for 1 or 2 minutes of your actual projects for Space Loom? Because I think it's interesting, but I know you're concerned about
Right.
tech transfer and everything.
Right. So what we are doing is generally the existing stratospheric balloons, they reach around up to 30-35 kilometer altitude. There is a fundamental existing physics doesn't allow the way existing balloons that higher than that. There are only 2 world records. In 1976, US had a world record of around 51 kilometer altitude reaching. And recently in 2003, JAXA from Japanese Aerospace, they have a world record of a balloon reaching 53 kilometer altitude in the mesosphere. But that's a one-time attempt. Their thickness of the balloon, what they do is, it's like a 3.7 micron. It's our hair is like 70 micron thick on an average. So it's very thin and delicate to handle, and you cannot manufacture any another thinner material than that. Even if you do maybe 1 kilometer higher, you can go. But the drastic change up to 80 kilometers, that's a totally different scenario. You cannot do with existing vessels. So what we are doing is we have developed new hardware and software changes that we understood. There should be an alternative way, not just to focus on lighter payload or lighter things to take it higher altitude, but to be better understanding the environment, the way we are doing ballooning and the environment in which we are doing ballooning. These are the things that we are focused on and developing this technology. Currently, we are already actually doing this, our technology demonstration testings right now. Yesterday, I was in the testing. Tomorrow also, I am in that testing. So in in let's say 6 to 8 months of time, it will be in public domain, much more open for how exactly this thing is expressing question. I'm being haunted by that question. Definitely, we will be showing the demonstration and you will know in more detail. Is that helpful?
Yeah, I know you can't say more than that, but I just want to add that this poor guy has, he is an example of being persistent with your aspirations. Okay, you just cannot give up. He has been working on this for years and years and years. He has had failures on the way. He has never given up. And I think his company is going to be very, very successful because he's working on an idea which has never been done before, which has the interest of a lot of space agencies, a lot of companies around the world. And I know he spoke with more than 100 or 200 people,
It's more than
including
1,500
astronauts.
now.
How many?
More than 1,500.
1,500 people just to get an idea, just to form. So the whole idea behind this is, again, for the students, things will not be handed to you on a silver platter. You have to work for it. You have to persist. And then if you keep on persisting your dreams, you will follow it. And John has said the same thing. Pradeep is doing the same thing. Nitya is going to do the same thing because he is focused on a topic which is close to his heart. And the only way you can be successful is to do something that's what you like. Pradeep and John, thank you. You are a shining example of this Florida Space Current program. And you are like ambassadors for us and for NASA.
Thank you for the honor.
Thank you.
Thank you. Thank you very much, Jaideep. Thank you again, Dr. Chinde. Ladies and gentlemen, I would like to take this opportunity to thank Dr. Jaideep. And along with Dr. Jaideep, there are a few very eminent men who have joined this webinar. I would like to thank Mr. Tim Dyer. Tim, thank you so much. We have made you as a co-host. We would request a few comments. I would like to express a sincere thanks to Mr. Professor Subhash Rizbut from the University of California, Davis, who has been a pillar of support for the inaugural program on 10th July. Our special thanks to Mr. Prakasha Rao. Mr. Prakasha Rao is a very senior scientist from ISRO, a very senior scientist who retired very recently. He has been pioneering very many projects of ISRO. We are really honored to have the presence of Mr. Tim Dyer, Mr. Subhash Rizbut, and Mr. Prakasha Rao for this webinar. Can I request a few comments from Tim, please? Tim, over to you, Tim.
This was a great seminar, like always. Your work is great, and Jagdeep is fantastic, and this is an important program. I think people have to consider your educational journey, and there was some mentions about the journey you take, and I presented on my journey a prior seminar. But what I want to make you consider that if you're going to get a bachelor's degree in a space technology, this is great. But I got my master's degree in material science from UC Davis, and this has really helped me in my career accelerate our career. And UC Davis is working on a few different master's programs, and people come from foreign countries. There could be some financial assistance as well. But if you look at the lifetime, you could make, in terms of US dollars, maybe $10,000 to $30,000 more per year because of a master's degree. So a lot of people get PhDs, that's important, but consider that just for a little extra time in school, you can get this degree, and it also will help open the door for more space or material science work. So I'm also interested in why students pursue advanced degrees, and maybe that could be another topic. But I think it's really been beneficial. And then UC Davis again has some programs, but there's other universities like University of Florida that do this type of thing. So consider you have a journey, and then also if you're in your journey and you've gone to a job, or maybe you don't like something, you can always go back to school. Life is a continuous process, so always consider education as an alternative if you want to get ahead. I think it's very good. And again, thank you, DV, for inviting me in another great show.
Thank you so much, Tim. Thank you. Can I request Professor Subhash Rizbut for your special comments, please? Over to you, Professor Subhash Rizbut. Professor Subhash Rizbut is a distinguished and celebrated professor in the Material Science and Engineering Department in the University of California, Davis. Over to you, Professor Subhash Risgood. I think Professor Subhash should be joining any time. May I request Mr. Prakash Rao, sir, Senior Scientist, ISRO. Mr. Prakash Rao, sir.
Thank you, Mr. Venkatgiri. I think
Thank you,
it has
sir.
been
Thank
a
you.
very nice program. First time I am participating in this Indo-American Youth Talent, whatever you are calling the workshop.
Yeah,
So,
yeah.
yeah, thank you very much. So, I have seen a very good enthusiastic participation and very excellent presentations from some of the youngsters. It's always nice to see youngsters coming up with new ideas, and I have seen Nitya's work, which is state of the art, and also Jonah and Pradeep's struggles, as Mr. Jaideep has rightly told, where you have to perspire, otherwise there is no way you can succeed without perspiration. So nice to see all these youngsters coming up, and with forums like Explore the Space supporting them, I am sure the Indo-US space exploration will go much higher, the cooperation will go much higher. Thank you.
Thank you, Mr. Prakash Rao, sir. Ladies and gentlemen, for those of you who are new, Mr. Prakash Rao had the great opportunity of guiding the senior scientists in ISRO like Mr. Veeramuthuvel, who was the project director for Chandrayaan-3, and Madam Shaji, who was the project director of Aditya. So Mr. Prakash Rao was guiding them and he was senior to them. So we are really happy to have somebody very senior like this. Thank you again, Mr. Prakash Rao, for joining this program.
Thank you.
May I request Professor Subhash Risgood for his comments, please? Professor Subhash, please.
Yeah. Well, yeah, I'm very glad to have this seminar I could attend to. I am sorry I got a little late attending, but it's a tremendous effort you guys are doing, DV, so I really appreciate it. And I look forward to further conversation with you about the IIT Bombay thing you requested, and also to see if some of the students from your orbit and ours here in the UC Davis system would, be interested in internships of some sort or the other, and we will certainly pursue that as we go along. Yeah. Thank you.
Thank you so much, Professor Subhash Risgood. Again, for those of you who are new, it is 6 a.m. for our friends in California.
Yeah.
When the program started. So thank you for joining. Before I pass it on to Professor Jaideep Mukherjee for final comments, I request a 1-minute comment by all the three speakers. Can we start with Nitya? Nitya, please.
Yes, I'm actually very thankful to you for giving me this opportunity, because today I could see so many professors, so many scientists, and I'm able to interact them, and I have, I get to know what they think about my research work. So actually, I would like to thank you for this opportunity.
Thank you, Nitya. We look forward to working with you. Now, may we request Madam Jonah, the celebrated author of a children's book, who is along with us today. Jonah, please.
I want to thank everybody for the opportunity to be here to speak about my research and my journey. It actually started in 2003, 20 years ago, where I was an aerospace scholar in Texas and worked on this Mission to Mars project as a student at NASA in Houston. So 20 years ago to now 20 years later, in pursuing my education from undergrad to a master's and currently in a PhD program, you just need to remember dreams do not have deadlines. You are your only barrier in life, and age is really not a factor if you're continuing working on that path. And just to remember, there are other people out there that are willing to help you. Sometimes you do hit a wall, but sometimes if you can't go through the door, there is an open window. and to continue on the path and go forward. I also want to let you know there are other life science programs, such as at the University of Florida. They do have, they're starting an online PhD program in microbiology. So is that something you want to look into as an opportunity to pursue your PhD online? They are just beginning to open that up to students. And you'll be able to do that as an international student. So the opportunities are slowly opening. There are opportunities to get involved into space biology activities as a result. But again, I want to thank everybody, especially being here to talk to everybody today and NASA Florida Space Grant and Dr. Mukherjee has been so integral in my growth in this program.
Thank you, Jonah. Thank you. Over to you, Dr. Shinde, please.
Yeah, hi. It was really great to be here. I'm really excited for this India-US initiative. I'm looking forward to work with most of them, if not all, in the upcoming future. And also like to thank, I do call itself Space Loon is born out of NASA Florida Space Grant. So it's great appreciated for that thing. What I can tell to the students is, if they believe something that they would like to do, a lot of situations will come, challenges will come, but what is important to them, if they stick to it, things can flourish for them. That's my understanding and learning recently. But that's all. It's great to be talking to all of you, and thank you for the opportunity.
Thank you, Dr. Shinde. May I request Dr. Jaideep Mukherjee for his final remarks, please. Over to you, Jaideep.
Okay, I want to show you one slide which talks to you about the global space economy. Hold on 1 second. Yeah. There you go. So the global space economy, look at the extreme left. In 2030, it's going to be almost $1 trillion. It's about $500 billion, $500 billion now. It is growing rapidly. Look at the private funding. That is also going up a lot. In the past, most of the funding for space came from government agencies. And even right now, it is the maximum funding comes from them. But the private funding is increasing slowly and slowly. So I expect the private sector to play a big role. NASA is embracing the private sector. ISRO is embracing the private sector. So, small. And when I talk about the private sector, I'm not talking about the huge companies like Blue Origin or SpaceX. I'm talking about small companies like Space Loon. In fact, if you look at what NASA does here at the Kennedy Space Center and the Space Coast, most of the manufacturers are very small companies. They are the ones who actually help the economy more than the SpaceX and Blue Origin. Look at the countries with space agencies. They've gone up to could be about 100 countries with space agencies in the next 5 or 6 years. What is exciting is a number of startup companies like Space Loon. In 2022, there was about 600 as compared to 250 in 2010. And the projected growth is 1,000. And I know in India, there are also a lot of startup companies coming up. They're working with ISRO. Same thing here in the US. There are a lot of startup companies. In fact, a number of our students who have gone through our programs have started their own companies. Pradeep Shinde is one of them. But Nitya, if you're interested, the company Made in Space, which made the first 3D printer in space, was founded by one of our space grant students. So now that company is bought by Redwire, and they do a lot of manufacturing in space. Again, I can get you in contact with that company so you can work with them, because the work that you're doing will be very, very interesting. And then again, if you look at the number of satellites, there are about 5,000 right now, and it's going to be more than 15,000. I'm not very happy with the number. As Nitya was talking about the space debris, we have SpaceX launching, hundreds of satellites every year. In fact, I live in Titusville, which is just across Kennedy Space Center, and I'm seeing a launch almost every week. In fact, time has come where I don't know when there's the next launch. I hear my windows rattling, and I know there's a rocket being launched. So there are so many satellites. And the cost of the satellites have come down from about, say, almost $1 billion to less than, $100,000 right now. So there is a huge role for everyone to play in the space sector. And look, here's an example of the global space economy, how it is mushrooming. And this graph shows you the different areas of the global space economy. Of course, the satellite launch is not the biggest one. There are other organizations, other projects which take up most of it. But the idea is that, you don't just have to build a rocket to be a part of the space program. You can come up with creating tools like Nithya is doing, or what Jonna is doing. I think what Jonna is doing and the project they're doing is so important because a lot of companies who are interested in space tourism. And if you want to, and they're going to create space hotels, orbiting the Earth or orbiting the moon. If you want to do that, you really want to figure out how these bacteria function under microgravity. So I know there's a lot of work going on at the University of Florida and in Florida and other places. That is another big topic to go. And here's some of the trends and innovations in 2023, from miniature satellites, advanced communications, smart propulsion, space data, space mining. Space mining will take some time. I've been hearing about space mining for the last 7-8 years. And the number of companies that came up, private companies, have all gone down under. They couldn't cope up. So that'll take some time. But I think if private companies are interested in mining asteroids, that will open up a lot of opportunities for students, because you have to figure out a way of reaching those asteroids quickly, a way of landing on the asteroids, a way of excavating the regolith from the asteroids or the minerals, bring them back to Earth. So that's going to create a huge opportunity in the next 10-15 years for students. These are some examples of companies that have come up who are working on the space global industry. This is a great time to be a part of the space economy. And I think the students who are here, you have taken the first step. I know you're going to be successful because you're interested as we join this program. And I've yet to see a student who has shown an interest in not being successful. I've yet to see one. So I would like to stop here because I think we have reached 10:30, and I like to always start and end on time. But Venkataragiri, thank you for doing this. I think as we go on with future such programs from different states, the students in India and the US will get a chance to see what's going on in different countries. And in the future, I will also encourage you to have at least one student from India and maybe 1 or 2 from the US, or 2 and 2, so that they get an idea of what's going on in each country. Thank you again for all your hard work.
Thank you. Thank you, Jaydeep. Ladies and gentlemen, with this, we come to the close of the second edition of Indo-US Youth Space Talent. I would like to convey my sincere thanks to Professor Manu Santanam and Professor Satyan Subaya for having facilitated the participation of Nithya from IIT Madras. Thank you so much. A special thanks to Jaydeep Mukherjee, who has been a great source of support for Explore the Space for many years now. Many thanks to you, Jaydeep. Thanks to the speakers, Nithya, Jonna Ocampo, and Dr. Pradeep Shinde for having made excellent presentations. As I mentioned, our special thanks and recognition for the 3 eminent men who have joined in our program today, Mr. Tim Dyer, Professor Subhash Risbut, and Mr. Prakash Rao. With this note, this program comes to a good close, and kindly watch out for more information about the next edition. Thank you all, and good night to friends in India, and good day for friends in the United States of America. Bye-bye.
Thank you.
Bye.